So today we are very happy to have Ning Su from Affiliation and Caltech. He's going to tell us how Bootstrap needs to scatter experimental data.
Thanks for the introduction and thanks to invite me to give this seminar. I'm going to talk about how to use the Bootstrap method to start.
Wait a minute. Silence!
I'm going to tell you how to use the Bootstrap method to study pion scattering. This work is based on my recent paper with Andrea Guerrero and Curlian. So Bootstrap is the method that we try to compute a physical quantity in a non-perturbative way, not referring to the Lagrangian. Instead, we're going to use a consistency condition, namely unitarity crossing and possibly another other symmetries. So in conformal Bootstrap, in the last few years, there are many interesting results come out from numerical Bootstrap. We developed many technical infrastructure, specifically powerful solvers to handle SDP. So in both conformal Bootstrap and S-matrix Bootstrap, we try to translate unitarity, crossing, and other constraints to highly non-trivial semi-definite program. And we have advanced numerical method to solve those SDP and make prediction for physical quantities. So in this talk, I'm going to tell you how to apply the SDP method to study pion scattering. So first, I will quickly tell you the basic idea and the main result. Then later I will tell you more technical detail. So the basic idea is that let's first think about unitarity. So unitarity is SS dagger equals to 1. This unitarity, how does this affect the S matrix? So if we consider 2 to 2 S matrix, 2 to 2 S matrix square plus 2 to N S matrix square totally should be equals to 1. So this S2 to 2 is the function depends on STU. This function has to be, so totally it should sum to 1. Therefore, if we only look at 2 to 2 S matrix square, it should be smaller than 1 on the physical region. So besides that, we also have crossing symmetry, analyticity, and isospin symmetry. So in this talk, I'm going to assume in the pion scattering, pion have exact isospin symmetry. Then let's think about the 2 to 2 S matrix. It depends on S and T. And the idea is that we can try to write down the ansatz to expand this S matrix to be some unknown coefficient AN times known function Fn depends on S and T. And we try to search for Sn such that this function obeys unitarity. So how to demand the unitarity? So if we want this function to be smaller than 1, this condition translates exactly to this statement as a 2 by 2 matrix. This 2 by 2 matrix, if we demand it to be positive semi-definite, that is exactly equivalent to the statement that S square should be smaller than 1. But this condition is a semi-definite condition. Therefore, we can use semi-definite program to solve it. So let me quickly review what is a semi-definite program. Semi-definite program is the following numerical problem. We have several matrix valued vector. So it's an n-component vector, but the entry of the vector is n by n symmetrical matrix. And we try to search for the n-dimensional numerical vector such that this alpha, this vector, dot all the matrix valued vector, the result is a matrix. And we demand this matrix to be semi-definite positive. And same alpha acting on all the vector should be positive. So that's the semi-definite program. And if alpha exists, we have a space of alpha that satisfies all the conditions. Then in this space of alpha, we might choose to maximize certain objective. So for example, we might try to maximize alpha dot b, and b is some known vector that you choose. And in order to do this, we also has to normalize alpha in some way. So we can normalize alpha dot some other vector equals to 1.
So M is not real.
M is real. M is a real symmetric matrix. So then if you this is SDP. Now let's go back to the S matrix problem. Once we have this condition has to be held for fixed S and T. So therefore we have multiple, not just one condition like this. We have many conditions like this at different value for S. Then that becomes semi-definite program. So far at this point we imposed unitarity. And we still has to impose crossing symmetry, analyticity, isospin symmetry on Fn. So for this, I'm going to talk about later. For now, let me just tell you the main idea and the main result. So the idea is that we try to impose all the theory constraints, unitarity, crossing, analyticity. And also we demand the S matrix we construct in the low energy should matches with the experimental input. So the experimental input is the pion to pion low energy scattering phase shift. So let me give you some example. In this 3 plot, that's the phase shift for spin 0, iso spin 0, spin 1, iso spin 1, spin 0, iso spin 2. And the horizontal axis is the S variable, but the unit is pion mass, m pion equals to 1. So for S equals to 50, 100, 200, that roughly corresponding to 1 GeV, 1.4 GeV, and 2 GeV. And the vertical axis is the phase shift of the S matrix. In those plot, you see those blue arrow bar. That's the experimental data.
So what do you say that this 50 is 2 GeV?
Hmm?
The biomass is 140.
The pion mass is 140. Yes.
With the bio 50. It's like 7 GeV.
Because you have to take this S is
sorry, take it back.
yeah.
So very good.
So those are from the experimental data, and the idea is that we try to construct the S matrix that satisfy all the constraints, both theory constraint and the experimental constraint. Once we have that, potentially we can take a look at this S matrix at a high energy and to see if we can make some prediction out of it. So in those plots, the blue are from experiment data, and the red is from the S matrix we constructed. So indeed we can construct the S matrix in the low energy matches with the experiment. Okay, so once we have that, we can take a look at those S matrices. For example, this is a plot that in spin 0, spin 1, iso spin 1, and that's the S matrix on the complex plane of S. So this is real S, this is imaginary S. Here you can see there are two 0 corresponding to two mesons. This is row meson. That's the next meson. Another interesting thing is if you look at the iso spin spin 0, iso spin 2 channel. So before I showed you this plot, so those are the orange error bar in this plot. That's the experimental input we demand has to be satisfied by the S matrix. But the blue line is our computation satisfy all the theory constraints. So if you just look at the low energy data, it's not obvious at all this phase shift should go up, but just out of our computation, it goes up. And then the rule of thumb is that if this phase cross 0, it should have a meson on the complex plane. So we look at the S matrix and go to the complex plane to actually find the 0. So that's the location of the this meson, the imaginary part and the real part of the mass. Therefore, the conclusion is out of this computation, it seems like we find a new meson. It's not in a particular data group. It's the iso spin 2 meson around to GeV. And since each quark have 1/2 iso spin, therefore this meson should at least have four quarks.
So this blue curve you obtain from the solution of your bootstrap problem.
Yes.
I have a related question. Sorry. How did you get qualities instead of inequalities? Usually the bootstrap gives you inequality.
Yes, it's inequality.
But then how did you get a definite value for S?
That's a good question. Let me rephrase your question. Since it's inequality, in principle, I can have many solutions.
Yeah.
How I find the unique solution. I'm going to tell you detail about that later. Roughly speaking, we are trying to select a solution that matches the low energy experiment the best.
There has to be problems that you minimize the
roughly. Okay, so now let me tell you the actual computations, the detail of the computation. So first, let me go through all the consistency conditions. So firstly, the S matrix depends on STU. We write it as 1 plus IT. And we have to impose S plus T plus U equals to 4. Remember the unit is M pi equals to 1. And we can decompose the amplitude. T depends on S and T, but we decompose to Legendre polynomial and we get spin. Then in terms of T, the unitarity is 2 times the imaginary part of T should be larger than T direct T for each spin. For all the spin, it should hold. or in terms of SL, it should be SL square should be smaller than 1 for all the spin. That's the unitarity. Then analyticity says SLS is analytical on the S plane, except the bench chart from 4 and also the image under crossing. Also, crossing symmetry says STO should be covariant on the STO exchange, but crossing symmetry will be mixed with isospin symmetry. So let me tell you isospin symmetry first. So isospin symmetry, pion. In this case, I will take O3 symmetry. So the difference between O3 and SO2 is not important here. So the pion is a vector representation for O3. So we have vector times vector. It should decompose to singlet and O3 antisymmetric tensor and symmetric tensor. So that's singlet. Singlet is isospin 0. Antisymmetric tensor isospin 1. Symmetric tensor isospin 2. Then this S matrix is not just a scalar function. Instead, it should carry the isospin tensor structure. So specifically, this should decompose to some tensor structure in isospin 0 times S matrix in isospin 0, etc. So for example, I had a typo here. So this should be isospin 0. So for example, this tensor structure for isospin 0 is just delta ij delta kl, and ijkl is the O3 index for the pion. Similarly, you can write down for these two. Let me say a few words about analyticity. Before I told you the analyticity is SL is analytical everywhere except the bench chart and the image. But for the image you have to for the image of the bench chart under crossing symmetry, you have to consider crossing symmetry. But for now, let's forget about crossing symmetry for a moment. Let's just ask the following question. If we want a function that is analytical everywhere, except from 4 to infinity, except this bench chart, how can we construct the ansatz for that crossing symmetry? So the basic idea is that we do this coordinate transformation from S to rho, and sigma is some number we choose. So we can choose sigma to be any number larger than 4. We can choose sigma to be 5 or 100. So for any number of sigma, we choose this coordinate transformation map S plane to the unit disk, and the branch chart becomes the boundary of this unit disk. Therefore, the analytic function on this unit disk is just a power series on rho. So this parameterizes the analytic function on the S plane, and we can take a different set of series for different sigma. That's our generic ansatz for the analytic function.
Sorry, sigma is somewhere in this picture.
Sigma is not in this picture, but
What if sigma doesn't control something about the disk or the map?
You choose any sigma, you get same. For different sigma, it's always a mapping from that plane to this disk. If the power series is infinitely bigger, I think they would be equivalent. But when we do image, we're going to try to put the power series. Then choose different sigma would be sensitive to different region.
So finite order in rho corresponds to what kind of functions of of S, it's powers of square roots. I'm trying to understand what, I'm trying to understand what is the actual ansatz of the truncated row. Can you unpack that a little bit for us? You're going to truncate in the series of rows,
Yes.
right?
Yes.
So what is that in terms of more standard variables? It's just
It's just
powers of square roots.
yes.
And should we have expected that? Should we have expected, or should we have thought that there could have been more complicated branch cuts other than square roots? More complicated functions?
Mm,
Or is that somehow a basis for all the branch cuts we could have had?
I think that's not the most generic answers for the branch cut. In my code, I actually try to also implement the branch cut, not just starting from 4, but other branch cut. For example, starting from higher value. That should, for example, can correspond to K on production. But still, this is still not the most generic one.
But aren't there also in the S matrix in general branch cuts that don't correspond to multi-particle thresholds? Not every branch cut corresponds to a multi-particle threshold. So
Or lots.
yeah. Why do we have such a restricted idea of what the
I'm not claiming this is the most generic answer for the branch cut. Well, let me put it in this way. This answer is probably good for low energy at least. But
why?
Hmm?
Why? Even at like a couple loop order in S matrix calculations, you in general find logs or other things. You also in general find branch cuts away from multi-particle thresholds. So even in perturbation theory, I think we know that we encounter more general branch cuts than that.
even at the low energy.
Well, at 4M.
Yeah.
Even at 4M. Work. Around 4M.
You're not really doing low energy.
You're
You
gonna
have
go
S from 4M squares to infinity.
Yeah, you're gonna go to, you want to go to beyond scalar perturbation theory, which is
Yes.
pretty handy.
Well, this should be good at least around the elastic cycle. And beyond that, we are going to choose different sigma, and in principle, I want to choose different different number for the start of the branch chart. So,
But I feel like it should be possible to improve this. So the function should be analytic in a row for row smaller than 1.
yes.
So but here your thing is analytic.
Yeah, it's an issue.
So if you truncate, right? So maybe you should allow yourself to have some things that are actually have analyticity that radius r equals 1.
One idea to improve this is I can write instead of using this ansatz, I can write row minus some number divided by 1 over row minus some number. That will parameterize correctly with the pole on second sheet. So the actual amplitude should look stuff like that. Looks almost like a CDV function. This ansatz will not have the right second sheet code. So I know it's fundamentally not right. It's just the hope is if we put a main term, it will simulate that.
How many A's?
I will tell you in a few slides.
For the lower energy matching, the leading branch cuts are probably logs, right? Rather than squares. Say 1 loop. Chiral perturbation theory. Does it match Well, okay, maybe you'll show us. I guess you will do the leading matching to the EFT.
No, I'm not going to do that. I'm going to match with the experiment.
You're not the lead EFT.
I'm not sure. Okay, so once we have this row, let's go back to the actual problem. Now the S matrix is we can write it as some function times the tensor structure. So we only have three tensor structure: delta ij delta kl, or delta ik delta jl, delta I L delta jk. And at the front, we have some function depends on STU. So the crossing symmetry says this term, the first term, should be symmetrical on the TU exchange. So that's the crossing symmetry. Now we want to combine the crossing symmetry with the analyticity and the isospin symmetry. So demanding this function symmetrical on the T and U, this translates in terms of real variable, this translates to this ansatz. So in this ansatz, you can already say it's explicitly symmetrical between T and U exchange. It's not the most generic one, because we also have to impose the constraint S plus T plus U equals to 4. So if you impose this, then we have this ansatz. And similarly, we have ansatz for other S function. Now, so far, this is ansatz for S depends on S and T and U. Those tensor structure is not the right tensor structure corresponding to different isospin. However, now we can relate those delta with the correct isospin tensor structure. So after that, we can translate all S matrices in different isospin related to those functions. So in a specific example, is isospin 1 function is related to those functions in this way. So you can imagine in the same way, I can write down S matrix for different isospin. So after this procedure, what do we get? We get the then once we have this S in different isospin, we decompose to different spin. Then we get S in different spin, in different isospin. The result can be written as sum of unknown coefficient times some function. So those functions are terms like this. So that's a known function already implemented analyticity, crossing symmetry, and isospin. Okay. Then each S, the condition is those S should be have norm smaller than 1 on the branch cut. So we have multiple conditions written in this form for isospin equals to 0, 1, 2, and for different spin and for different S. Then we try to search unknown coefficient A and B to actually find those S. So any questions? So what I told you is what Brary and Donis they did a few years ago in this paper. So what they did in that paper is in addition to those constraints, they also make an extra assumption, which is the existence of the order zero. So the order zero is that when you do current perturbation theory, in the first order, in the amplitude, you will observe the amplitude having a zero below for m squared, for spin 0 and spin 2. So this 2 0 is called order 0. In chiral perturbation theory, the 0 is at 1/2 and 2. So in this paper, what they did is they assume this order 0 should exist, namely using this condition to solve two of the unknown coefficient, and then search for the amplitude. So the result is the following. For each choice of order 0, for each choice of, you can construct an SDP, and you ask, would you find those A and B, those unknown coefficients that satisfy all the constraints? The conclusion is that in this plot, in the blue region, in the shaded region, you can explicitly construct those unknown coefficients, satisfy all the constraints. But in this white lake, you cannot find such coefficient. Of course, this is not a rigorous bootstrap bound. So in conformal bootstrap, we often say it's rigorous, but in this case, it's not, because we have an ansatz that is not rigorous. However, they checked as you increase ansatz to be larger and larger, this lake basically converged. Here you can see the multiple curve. So so it basically ruled out the leading order perturbation theory result. Okay, so that's the old result. So what we did is we instead we demand in the low energy it should satisfy experimental result. But let me tell you a little bit how people analyze, how people find the meson in particle scattering experiment. So usually people start with some model. And this model might have some theory constraint built in. For example, typically, it might have partial forcing symmetry built in, or partial analyticity built in. Then this model have some tunable parameter. Then you tune this parameter to match experiment in the low energy. And after this procedure, the model gives you a unique analytical continuation of the S matrix to the complex plane. Then you go to the complex plane and find the pole and rid of the meson. That's the procedure. Of course, this different model would give you a different analytical continuation, and that would lead to different meson mass. Actually, that's the biggest source of error bar in PDG. For example, in this plot I showed you here, that's the iso spin 0 S matrix on the complex plane. Horizontal axis is real S. Vertical axis is imaginary S. Here you see multiple cycle. Each cycle corresponding to a paper. So each cycle is coming from a model that try to fit with experiment in the low energy. Since in the experimental data have some error bar, therefore this fitting will give you some error bar. So the size of this cycle corresponding to the error bar come from the error bar in the experimental data. But different cycle coming from different model. So different model give you different fitting. And in PDG, what they do is they take all analysis and do some average. So if you look at here, many of the cycle even doesn't agree with each other. So that's what people do in experiment. So then if we think about this position, what we really should do is that we should do similar thing, but we should impose the model independent ansatz and try to do it in the generic way and try to impose all the theory constraints. But this would be essentially try to do Bootstrap. So in some sense, what I'm trying to do is similar to what experimentalists trying to do, except now we try to impose the most generic theory constraint. And this could be the right way to analyze the data. Okay. So let's go back to the Bootstrap approach. So the input are the lower energy data, and we try to do this Bootstrap procedure. Now, okay. Now that is the question. How do we construct a unique S matrix? Assuming we have multiple solutions, both satisfies all the constraints, how can we select one that matches the experiment as much as possible? So the basic idea, there are two ideas. One idea is that we can scan over some parameter. So those parameters could be the order 0, could be some location of the meson. So we can demand that this S matrix have a 0 at a certain point of the complex range, and use this condition to solve two unknown variables in the ansatz. So that's something we can impose. And we can scan over those parameters. For different parameters, we get different solutions. And we try to, we can define a fitness score, measure how close our S matrix compare with experimental data. So we can try to scan over different parameters and try to find the best fit. That is another idea, another approach. So actually, we can also encode the experimental data into the objective of the semi-definite program. The basic idea is, let's consider this expression. That's the norm of the ansatz, S matrix ansatz. And here is cosine the phase of the ansatz minus the phase shift of the experimental data. So if you maximize this expression, that will force the phase of the ansatz matches with the phase of the experiment. But this expression can be written in this way. So it's imaginary part of the ansatz times sine. This phi is the experimental phi, and same thing. So then the ansatz is written as it's linear in those unknown coefficients. Therefore, this whole objective is linear in those unknown coefficients A and B. So we can put this into the semi-definite program. And this objective should sum over different S value. So once we put in this objective, and when you maximize this objective, the SDP will try to construct an S matrix that matches with the phase as much as possible.
Sum over these S values, they're
Yes.
treating them equally.
So in my computation, I discretize them equally. Probably that might not be the best approach, but The another idea, roughly speaking, you can construct another objective. Okay, so back to the work done by Andrea a few years ago. They checked that if you look at the low energy scattering length, so those A is the S matrix expand around 4, and then A is the leading coefficient. So A11 is isospin 1, spin 1, isospin 1, and A02 is spin 0, isospin 2. So those coefficients you can try to check in which region those coefficients are allowed. Then that's the plot. It is only allowed in the shaded region, and the white part is excluded. And this is roughly the experimental result. So that is a change. But by doing this, they fixed some other parameter. So this is a slice on the allowed region. And the experiment data is roughly on this change. So another idea to construct a unique S matrix is that we can try to minimize those coefficients. Minimize those coefficients towards certain direction to get a unique solution. Basically, we go to boundary of the allowed region. Okay, so in our computation, we tried various ideas of them. Different idea would give you slightly different S matrix, but in all the computation, we observed the existence of this isosymmetry meson. Okay, so for actual numerics, we used more than 500 terms in this ansatz, and we imposed this condition, unitarity condition, for spin up to 12 at 350 different S values, and then what we missed is the unitarity condition for larger spin. But to compensate for that, we impose linear unitarity. So imaginary part of T should be positive. This is imposed for different discrete S and T value. Just try to, because if we don't impose this one, then in principle we should include all the spin. So this linear unitarity turns out to be quite important. We should not miss it. So that's the S matrix we constructed. And now let's take a look at the actual S matrix. In this plot, that's the isospin 0, spin 0 channel. Red and blue corresponding to a real and imaginary part of the S matrix. And each wave you see corresponding to a meson. So for fixed spin, there are actually infinite number of meson production. And here, this corresponding to the sigma meson. This plot is spin 1, isospin 1 sector. And this sharp shape corresponding to the row meson. Okay. So, this is just from one computation. So, in our paper, the result present in our paper is that we did many computation, try to optimize over the ordered 0 and the location of the low energy meson. That's our search parameter. So we have a bigger maybe in a high dimensional parameter space, including all those parameters. And we run multiple simulation in this parameter and try to try to match low energy data as much as possible. And out of this computation, that's our best estimation for the sigma meson in the complexity. This result still carry statistical error bar, so it's not the same as the conformal bootstrap result. It's not a rigorous bound. But out of it, we matched multiple meson in the PDG.
Sorry, can you just elaborate on why you don't get rigorous results? I'm not quite understanding what the difference is to the conformal bootstrap. You have strict inequalities, and you have linear functionals that vanish on that have some definite sign on the ignored coefficients or not.
Okay, good. So in Bootstrap, there are two different methods. So in typical conformal Bootstrap, what we are trying to do is we try to show the posing symmetry. We first try to take the function to find the dimension. Let's imagine conformal Bootstrap. We write down the Bootstrap version, which is posing symmetry. We try to take that to find the dimension and try to show certain choice of spectrum is in contradiction with that function. So we try to show in finite dimension, certain choice of parameter cannot be true. That's the rigorous approach, because if the function cannot hold at finite dimension, it cannot hold in infinite dimension. Instead, here we are doing something different. Here we are trying to check certain spectrum. We are trying to construct an approximate solution to the truncated setup. So basically, this is called the primary approach. You have some truncation of the equation, and you try to find an approximate solution to it. This is not rigorous, because if the equation holds in finite dimension, it doesn't mean it's holding in infinite dimension. But if you show it doesn't hold in finite dimension, then it cannot hold in infinite dimension. So that's the rigorous approach. Here we are doing the approximate solution approach.
So the exterior of your blue region is still allowed.
It might be. It might be wrong.
The space of all solutions that solve the equation will be slightly bigger than that.
Yeah. So essentially, this approach is starting from the allowed region and try to push towards the boundary of the allowed region. Now the approach is from outside to try to yeah.
But why should the actual solution be near the boundary of the allowed region? I don't see any reason for that.
No, so actual solution should be inside.
I was just reacting to what you said. You said you were pushing towards the boundary.
Okay, so we have infinite number of constraints, right? But to do numerics, we can only do a finite projection of this constraint. Right. So then we have two approaches to do it. One approach is we construct a approximate solution to this finite number of constraints. Another approach is giving some assumption of the parameter, we try to construct a contradiction with the finite number of constraints. So the first approach is not rigorous. We are trying to construct a solution. Second approach is we are trying to exclude some solution. The second approach is rigorous, but first approach is not. Okay, so
Sorry, what role do inequalities play? I'm a little bit confused. So an analytic function is determined by knowing it in an open set. So if you just say that you're gonna find an analytic function that matches the experimental data, why do you need the inequalities? Well, why can't you just write some ansatz for this analytic function? You try to minimize the difference between that and the experimental data. There's a unique analytic function that actually fits the exact data if you happen to know it.
that's roughly what we are doing, except we also has to require an satisfy unitarity. We want to impose all possible constraints. Roughly, we are trying to construct an analytic function with a low energy match with experiment, but at the same time, we want to maintain unitarity.
But just a priori, if you knew the low energy, you do not, but if you had exact infinite precision knowledge of the low energy S matrix, infinite precision, then you could just say that I want an analytic function that has that property at low energies, and the answer would be unique, just based on analyticity. You would not actually, it would come out to be unitary.
Yeah.
So I'm just trying to understand in your, I don't really understand what the bootstrap is pointing to exactly.
Your question is, what does the bootstrap do?
Yeah, why do you even write these inequalities? Why don't you just find some central value of this analytic function and approximate it with your ansatz and see what the output is?
Okay. So, what you are saying is, why not we just construct an analytic function match with those and forget about the
Yes.
unitarity. If we do this, it will easily violate the unitarity at larger energy.
Only because of the uncertainty.
It will easily violate. In fact, it's very non-trivial to construct the estimation satisfy all the constraints and also match its experiment. And by demand, in all energy scale, it satisfies the theory constraint. Our hope is we get a little bit stronger predicting power at higher energy. For example, let me if we just look at this plot. Now, usually you would expect this will continue to go down, but in our computation, it goes up. Okay, so also
I was wondering, before the red line, was printing the upper.
So in this experiment data, it's actually two sets of data. One data go in this way, another data go in this way. So why we have two sets? Because there is no raw pion stacking. The pion stacking data is actually coming from pion nuclear stacking. It's an extrapolation of that procedure. Then it's already there are some final model appears there. Depends on which final model you use. One way you get this set of data. In other way you get this set. But now we have this numerical bootstrap tool. We can try to ask, can we fit both? I can definitely fit this behavior, but I try to not use this one. Instead, just use the lower one. Try to fit in this behavior. I can't fit it. So the conclusion is probably this is not correct. So in some ways, this is like.
What if you put more parameters?
Oh, that's a good question. I'm going to try to answer that in the next slide. What happens if I include a lot of okay, so I just want to.
What do these experiments say about each other? Forget about. I mean, they seem to exclude each other. So, what is the actual discussion?
Maybe I should say you probably had the impression you conform bootstrap everything is so rigorous. So we have a strong statement. but that's very rare in science. In science, this is more common. You have some final model, it's not clear.
Famously, the conformal bootstrap ruled out the space station experiments about the O2 model, so I'm familiar with that, but I'm just trying to understand even like, what are these two distant experiments that are so?
But I think it's the modeling, right?
It's model and
It's like the neutron, that's the experiment. I think they agree with the experiment, it's the same experiment. It's the
Yes,
Same
yes.
experiment,
Yes.
but what are the two plots then? Yeah. What are the two data?
That's come from different, this is pion scattering, but it's an extrapolation of pion nuclear scattering data. Then depends on how you extrapolate, you get different result. That's already model dependent. Ideally, if we can use Bootstrap to directly analyze the pion nuclear scattering, that would be fantastic, but right now we haven't been able to do it.
But
And
it should.
it should be
It
possible.
should be.
Okay, the last prediction is the isospin 2.
Here, you take into account the non-analyticity around the 4m square. So then you have a resonance like rho and F naught, but they don't contribute to the extra non-analyticity because they have broad resonance and have a large width. I guess.
They don't contribute to.
To non-analyticity at the higher ends. At their mass ratio because they are broad resonance and have a large width.
What is the?
I thought in your analysis you somehow not remove, but I can remove the non-analyticity at the S equal 4m squared by defining a new variable. So then there's a question about what about the effect of higher resonance, like the rho and sigma and so. Which probably doesn't contribute to analysis because they have large width and won't contribute to the actual non-analysis.
Isn't it on a different sheet? This. Are the unstable resonances in your picture on different sheets?
So those resonances are the whole on second sheet.
Right. I think that's so interesting. Also, there. He's trying to predict the completion.
Okay. Let me try to answer your question. What happens if we include more term in the answers? So, the ideal scenario would be like in conformal bootstrap. If we add more term, it's more sensitive to. We get a more predictive power at a larger energy. But in practice, that doesn't work. In fact, I haven't tell you the important constraint. This constraint is the sparseness of the meson spectrum. Namely, we actually should impose another constraint is in this region we should only have 2 meson. Or in isospin spin 0 isospin 1, we should only have this 3 meson and no other meson. However, right now, if we include a lot of terms in the answers, and we do this computation, what happens is that the semi-definite program will try to fine-tune those higher order terms. So we'll include a lot of higher order terms. In principle, those higher order terms should carry smaller coefficient, but in semi-definite program, after we run the optimization, the coefficient might get very big. Try to fine-tune those high order terms in order to overfitting low energy data. In that way, what we observe is it will violate the sparseness condition. It will generate some fake meson close to the bench chart. So ideally, this condition is roughly the analog of the gap assumption in conformal bootstrap. So in conformal bootstrap, we have to assume Rho and sigma are the only relevant operator. Namely, the next operator is larger than 3. So that's the sparseness of the relevant operator. But here, we should have some analog of that, which is sparseness of the meson spectrum. However, this condition is hard to impose. The reason is it's non-convex. If we have a solution whose S matrix is 1, not a solution, the S matrix is -1, you add up these two solutions, you get 0. Therefore, positive linear combination of solution is not a solution. So that means this condition is non-convex, and we cannot, since it's non-convex, it's impossible to impose in standard SDP. But there is still a way to impose it, probably in multiple ways. And right now I'm trying to modify the SDP algorithm to be able to do this non-convex problem. Yeah, that's roughly the story. In last 1 minute, let me tell you the interesting thing. After we post our paper, someone told us so actually this guy analyzed isospin 2 data for the at slightly larger energy. So those orange alpha is our input, but the purple is from this paper. Indeed, you see it increase. So we don't know this purple dot at all, but it just turns out it's probably correct. So in the future, it's probably interesting to say if we can find the isospin 2 meson
Sorry, but could you repeat what happened? So the data from 1973, but was not analyzed at higher energy.
I haven't looked at it carefully, but it's just there's some claim in the paper the phase should go up. Actually, so this is a recent paper also analyzed that. They said the phase shift should change sign, and this requires some underlying physics to change the sign, such as presence of resonance. So it would be interesting to say if this can be detected. There are two possible procedures for that from meson decay. In this meson decay, in principle, they can detect isospin 2 meson. We talked to some experimentalists to say if they can try to do this fitting. Yeah, thanks. So, this is going to be, I actually don't understand the process, but I'm just telling you what's it. Roughly speaking, they have this decay process, and in this decay process, they can take pions that amplitude as the input to the non-power simulation. And what they eventually want to simulate is the decay event. So, in fact, from this decay, they can extract rho sigma those level out of it. And we can give them all an amplitude and ask them to check whether it's compatible with the decay experiment. But since not putting isospin 2 meson there, they can already create experiment. Then it's likely it's not that sensitive to isospin 2 meson. I asked the various people, they said the number of events are strongly affected by low energy level. And those high energy levels change the event number by a little bit. They need to accumulate a lot of data to be able to tell. And it seems they don't have that many data to be able to tell.